Okay, let's look at number 2. Given that n is a positive integer greater than 2, that u of n be the set of non-zero numbers in Zn that are relatively prime to n. Here's the definition of relatively prime. If they're relatively prime, if there's no prime number that divides both of them. Here's the following list of propositions prove that u of n is a group under the operation of multiplication mod of n. In your proof, you must justify each step by citing an appropriate proposition from the following list. Now, I found that people got confused with what needs to be proved. And maybe it's a good idea to start stating what you actually need to prove before you prove it. So let's go ahead and do that. So you know the properties that you want to prove are, you have to prove closure, identity, inverse, and associative. Okay. So first we do closure. So let me state what you need to prove here. What you need to prove, maybe you should do it this way, because I find people sometimes state what needs to be proved and it looks like part of the proof. But if you put to prove at the top, then it's very clear what the role of this is. So to prove closure, you want to say given, well, let's see, our group, what are we calling our group? We're calling our group of u is u of n. So let's say given A and B in u of n, then A, now what's the operation? The operation is this circle dot. I'm just going to use the @ sign, okay? So I don't have to worry about formatting. So that's my operation. If A and B are in n, then A and B is also in u of n. That's what you need to prove. Now please keep that in mind. All right? So people kind of start in the middle and didn't do the whole thing. You have to start with this statement, given A and B in u of n, and then you have to show that A at B is also in u of n. Again, the at here signifies this circle dot that I don't want to bother making. All right, now, how are we going to use this proposition? So here, let's just put proof. So I'll start off with this same statement, given A, B, and u of n. So let's start with that. Okay. Now, what do we want to show? We want to get A at B. All right. So how can we do that with these propositions? Well, here's a proposition that involves the operation of two things, but there's not an A and a B here. There's a mod AN and a mod BN. So how can I apply this proposition to A and B? Well, look at the proposition right above. Here it says that if A is between 0 and n, then mod AN equal A. So bingo. I know if A is in u of n, then it's between 0 and n. So I can replace A with mod AN. And then I can apply this down here. Now, a lot of people just started with this, but that's not what you need to prove. You need to show that if A is in u of n, then this equation holds. Right? So what I'm going to do here is say, then A and B, then A equals mod AN, and B equals mod BN, since 0, let's do this, less than or equal to AB, I better not underline that, less than N. And this is by proposition 2. Okay, I'll just put 2 here, because I don't have room. Okay, so I've made a statement that follows from this based on a proposition. Okay, so, and from that, here, let's do this. I think it will work. If I do this, equals like that, and it will probably go like that. Okay, so then the next one, next implication, as I said, I can use this statement here. So that means that mod AN, and I'm using the @ sign, mod BN, is equal to mod AB. Okay? And then this is by 3. Okay. Now all I need to do is show that this number is between 0 and n, first of all, and then I need to show that it's relatively prime to n. Okay? So mod AB n is between 0 and n. And what does that follow from? It follows from this. Right? Where 0 is where you always get the mod is some number between 0 and n. So that follows from 1. Okay, let's get that down here. So that's from 1. And now I need to show that this number here, mod ABN, is relatively prime to n. Okay. Now what about AB? Okay. AB is relatively prime to n. Okay. Now what does that follow from? Well, let's see if we have a proposition that gives us Euclid's lemma. If a prime number divides AB, it must either divide A or it must divide B. Right? So because neither A nor B is divisible by n, that means that AB is not divisible by n. So this follows from 4. But I have not quite done. I need that this number mod ABN is relatively prime to n. So we have mod ABN. Well, how can we get it that mod ABN equals AB is equal to AB minus Kn for some value of n? Right. So that's what I can say here. Kn for some value of k. And that's here. That's also 1. Now I want to get that mod AB and AB, I know that AB is relatively prime to n, and I want mod AB is also relatively prime to n. And I can argue this way. I can say mod AB n is relatively prime to n, because otherwise I could rearrange this equation here and I could get mod AB plus Kn is equal to AB. Now if this was if mod ABN was not relatively prime to n, then this sum would also be not relatively prime to n. So otherwise, AB would not be relatively prime to n. Right, it might be better if I wrote more steps, but this does give the idea, that if mod AB were not relatively prime to n, then this would not be relatively prime, this not relatively prime to n, so the sum is not relatively prime. Then AB would not be relatively prime. But I know that AB is relatively prime. So this contradicts. Now instead of doing these arrows here, let me put numbers here, and that will be clearer, I think. Let's do numbers. All right. So this would contradict this 4 above. Okay. So I have mod AB and mod ABN is relatively prime to n, and it's between 0 and n. So that means that mod ABN is in U of n. So mod ABN is in U of n. And that follows from 3, because it's in the right range, and 6. Okay. All right, so you can do it this way. All right, so that gives me closure. Let's go ahead and do the next one, which would be identity, which is not nearly as long. And it's not going out. I don't know why. We'll just do this, I suppose. Okay. So I'll do 2, closure. I'm sorry, identity. Now, what is the identity of U of n? It should be 1. So let's see how that works out. In fact, I can do something very similar here. I can take 1 at A, or let me say, so I want to show given any, okay, so let me just do this the same way to prove that there exists 1 in U, let's say E in U of n, just to do it most general way, such that E at A equals A at E equals A for all A in U of N. Right? That's what I want to prove. So as I said, it seems to me that because people are getting confused, it's better to state that up front. Okay, so let's do the proof. All right, so what is this entry E? This E is going to be 1. Okay, let E equal 1. Right? Now 1 is in U of N. Since 1 is between 0 and N, and since 1 is between 0 and N, and 1 is relatively prime to N. Okay, so 1 is in U of N. So let's go ahead and find this. So let's do 1 at A. Well, what is 1 at A? Well, go up here. 1 at A is going to be, well, I know that 1 is equal to mod of 1n. I'm going to do the same thing I did before because I want to apply this same statement here. Okay. So 1 at A is equal to mod 1a, so at mod an. And this follows from the fact that, where is it? Oh, it's up here. This follows from the fact that both 1 and A are between 0 and N, and they're both relatively prime. So they're both equal to their mods, and then I'm using this fact 3. So I'm converting the numbers 1 and A to their mods by part 2, and then I'm converting the product using part 3. Well, actually, I didn't even use part 3 yet, so this is from part 2. Right. Then part 3 gives me that mod 1n at mod an is equal to mod 1a. Now, this is conventional multiplication. Right? Go back to part 3, and you'll see that part 3 is talking about finding the mod using conventional multiplication. Conventional multiplication right here, right? This AB is conventional multiplication. Okay? But 1A is just A. Okay? So this is equal to mod AN, and that's equal to A. Okay? This is also by part, so this is by ordinary arithmetic, and then this is by part 2, because I know that A is equal to mod AN. So this is by part 2. Okay? So in summary, I've shown that 1 at A equals to A. Okay? A similar proof shows A at 1 is equal to A. So that therefore 1 is the identity of U of N. Okay? So that finishes the identity proof. All right, let's go ahead and do inverse. Okay, now what do we want to prove? To prove for any A in U of N, there exists, let me just call it B because, well, I'll say A inverse, that's fine, in U of N, such that A at A inverse equals A inverse at A is equal to 1. All right, I can say 1 here because I've already established that 1 is the identity. All right, so this is what you want to prove. Please keep in mind what you want to prove. For any A in U of N, there exists an A inverse. Now, you can't just say A inverse and say, well, A inverse always multiplies A to give 1, because you haven't shown that there is an A inverse. You haven't shown what this is. You have to show that there is an element in U of N that satisfies these conditions. Right? So let's go back up and see the theorems that we have and see what we're going to be able to use. All right. Well, in this case, we're going to want to use this Diophantine equation here. This Diophantine equation, an plus bn equals c, has solutions for m and n if and only if c is a multiple of GCD of ab. All right, so let's figure out what we want to do here. Well, it turns out that if we do let our a here be the a that we're looking at and the n be the n that we're looking at here, then well, actually, we have to replace this because we have the condition that a and n are relatively prime, right? And here you have that there's a solution if c is a multiple of the GCD of a and b. Okay. So let me just take this down so we have it in. We have this down here, and then we have it handy. Okay, so let's go ahead and do the proof. Okay, so 4 states. Let's put it here. All right, so let's see what we want to do here. Now, when we want to get an inverse, we want the thing on the right-hand side to be 1. So I'm going to say let c equal 1. All right. Now, what else do I want to do? A is equal to a, but here we're looking at the multiple of GCD of a and b. So I'm going to let. So let's just say it this way to be clear. We'll replace c with 1, and we'll replace b with n, and then let's replace m and n with x and y. All right. If we do this, then I think it will be our application will be clearer. Okay. So let's restate the Diophantine equation. So there you have a 4 restatement. The restatement would be, I'm just going to replace the letters now. The Diophantine equation, a, now I said I'm going to replace m with x, and b with n, and n with y. So ax plus ny equals c. Now here c is 1, remember? So let's continue to replace. And we're replacing the m with x. You see m with x and n with y. So we'll change this to x, this to y. And here it says if and only if c, and c is 1 in this case, and only if 1 is a multiple of GCD of a and b. Now what does it mean that 1 is a multiple of GCD of a and b? Well, GCD of a and b is the greatest common divisor. It's the largest factor of a and b. Now, if 1 is a multiple of the largest common factor, that means that they have no common factors. And that means that a and b are relatively prime. Now, remember, we're replacing b with n. So that means that a and n are relatively prime. Okay. So a and n are relatively prime. That means that a is in u of n. That's the definition of u of n. Go back up here and see that. Right? U of n is the set of non-zero numbers in Zn that are relatively prime to n. Now we know that a is in Zn, and a is relatively prime to n. So this is staying down here. We've covered a lot of ground, haven't we? So if and only if a is in U of n. Okay. All right. So this is the so let's recap here. So let's make this point 1. Okay. And then let's make this point 2. This gives 4, okay. All right, so we know now that this equation, ax plus ny equals and has solutions for x and y, if and only if a is in u of n. Now, what does this equation imply? The important thing to look at is this x. Let's rearrange this, and let's put the ny on the other side. And we'll say ax equals 1 minus ny. And well, let's say that. Now, what's another way of saying that? Or AX is equivalent to, I'll write equivalent this way, 1 mod n. Okay. Now see, that's starting to look like inverse. Okay. Now the only thing that, so this is just rearrangement. Okay. The only thing that we need now is for x to be between 0 and n, and we need x to be relatively prime to n, because we need to show that x itself is now in u of n. Now, we can't guarantee that x is in u of n, but we could take mod of x comma n. If we take mod of x comma n, then that's definitely between 0 and n, and all we'll need to do is show that x is relatively prime. So let's do that. We'll say, let's say, let z equal mod of xn. Okay. Then let's look at what happens with a, and I'll use the at sign again for my multiplication. What is a at z going to be? Well, that's going to be equal to, you see that z is mod x comma n, so in this case, mod of z comma n is going to be z. So we're going to use this same thing here that we've done before. Right, we'll use 2. We'll use 2 because mod z comma n is equal to z. And then we'll use 3 because we'll be taking the product of the mod things and get the mod of the result. So let's go down here and finish that. Oops, sorry. I'm still here. Okay, so then mod a at z is equal to mod a n at mod z n, and then this is equal to, let me put it down this way. And this is equal to mod az n Now, what about mod azn? Well, z is modular equivalent to x. So that's equal to, it's the same thing as mod of axn, which is equal to 1. Okay. All right, so let's go backtrack and make sure we have all the reasoning here. So I'm letting z equal mod x of n. That's fine because I'm making my definition of z. Then a at z equals mod a n at mod zn, and this is by which one was it? I think it's 1. It's 2, right? Because we're looking between 0 and n, so it's by 2. And then this one is by 3. And then this one, saying that mod azn equals mod axn, that's by the definition of modular. Right. Okay. And then that's equal to 1. That's equal to 1 by part 3. Okay. All right, so I have a at z equal to 1. All right, so I'm not quite done. I've shown so far that for any a in u of n, I can find a z such that a at z is equal to 1. Now I need to show that z at a is also equal to 1. Z at a, and I can just copy this argument, right, and replace the z and the a since it's this way. And I can do this, and I can do this, and I have that. Okay. I guess this is my number 5. And then, so we have, in summary, for any a in u of n, we can find a z in U of n such that az equals za equals 1. All right? Now, did I cover all the bases? The one thing I have not shown is that z is relatively prime to n. Oh, and I should fix this up. That should be a at z, and this should be z at a. So far I haven't proven this, so let me take this out here. Okay. And I need to show that z is actually in U of n, so I'll put a 6 here, and then let's see how we can do that. Well, what does it mean that z at a equal to 1? That means that z times I equals 1 plus kn. Implies that za equals 1 plus kn. And I can write this as za minus kn equal to 1. And we know from this statement up here that this equation has a solution if and only if c is a multiple of GCD. In this case, c is 1. That means that z and n must be relatively prime. Okay? And that's by statement, I guess it was statement 4, right? Let's make sure it's statement 4. Which implies z is in U of n. All right, so the argument may be a little rough around the edges. Let's go backtrack and see what we have here and make sure each step is in order. All right, so remember, we're trying to show inverse. And we started with this fact that was one of the givens in the problem, that the Diophantine equation has solutions for m and n if and only if c is a multiple of GCD of a and b. Now, in order to apply this fact, we had to replace letters. And we now have this statement here where we have our given a, and we have our base n, and here we've replaced with 1. And this statement, this has solutions for x and y, if and only if a is in U of n, which is our hypothesis. And then we go through and we want to show that that mod of xn is actually the inverse of a. So we have this, so we did this, so x is equivalent to 1, and then we take the mod, then we show that in fact a at z is 1, and then we showed z at a was 1. And then we showed actually that z was in U of n. All right, so we finally got our inverse. Now my proof could possibly do a little rewriting just to make it to smooth off the rough edges, but the outline is there. I do have all the steps needed to show that I have an inverse for any a in U of z. All right. So last one we have now is associative. So again, let's write down what we have to prove. So this means given a, b, c in U of n, then we'll do it this way, a at b at c is equal to a at b at c. Right, and this is what we need to prove. So let's go ahead with the proof. Okay. So let's say, so here we have, just repeat this, given ABC in U of n. And we're going to use this same structure that we've used here. In order to get a at b at c, we'll use this fact that, well, let's just go at it. So let's do number 1. We'll have a at b at C is equal to mod of AN at mod of BN at mod of Cn. And this was by this fact, I keep forgetting, the fact that if you're between 0 and n, then the number is equal to its mod. And where was that? I'll go back up and see. That's this here. No, it's number 2. Okay. So I'll just continue the equality. Oh, I put 2 there, it's all right. And that's equal to, here we can do our combination here. That's equal to mod AB n at mod Cn. And that's by, well, I guess that's by 3. And then we say that's equal to mod ABC n. And that's also by 3, right? Because we're just multiplying the two things on the left-hand side. And therefore we can similarly, we can find that the other way, instead of putting the parentheses this way, we can put the parentheses the other way. So in summary, in conclusion, I can show that this here is equal to this here by substitution. And that gives me associative. And that's it for the proof.